Welcome everyone to this session, Caffeine's Great Escape, the Invisible Forces of Extraction. Today we will explore one of chemistry's most fascinating tricks, how we separate molecules at the microscopic level. Extraction may look simple in the lab, but behind it lies a story of molecular choice and preference. To make this concrete, we will follow caffeine, a molecule that most of us encounter every morning in coffee or tea, as it makes its great escape from water into an organic solvent. Extraction is essentially the story of molecular escape. Molecules are not randomly scattered, they are selective about where they want to live. Each molecule chooses the solvent where it feels most at home. This preference is what allows us to separate and purify compounds. For caffeine, the journey is dramatic. Given the option, it leaves water and bolts for dichloromethane, an organic solvent. This choice, invisible to the naked eye, drives the entire process of separation. At its core, extraction is simply a separation technique, but an incredibly powerful one. The process is driven by solubility differences. A compound may dissolve reasonably well in water but much better in another solvent. To make this work in practice, we need two solvents that do not mix with each other. We call them immiscible. The classic example is oil and water. In the laboratory, one solvent is usually very polar, water, and the other is less polar, an organic solvent such as dichloromethane. Here's the chemistry rule: like dissolves like. Water, with a dielectric constant around 80, is highly polar. It loves ions, salts, and strongly polar molecules. Organic solvents like dichloromethane, or DCM, are moderately polar, with a dielectric constant around 9. They favor neutral, slightly polar, or nonpolar compounds. Caffeine is neutral overall, with both polar groups and nonpolar rings. But look at the numbers. Solubility in water is about 22 mg per milliliter, while in DCM it's about 140 mg per milliliter. No wonder caffeine makes its escape to DCM. Now consider caffeine. It is not an ion, it is neutral overall, but it has both polar groups like nitrogens and oxygens, and nonpolar parts, its carbon rings. It is caught between worlds. But on balance, it finds dichloromethane more comfortable than water. In fact, its solubility in water is only about 22 mg per milliliter, whereas in DCM it skyrockets to about 140 mg per milliliter. That enormous difference is why caffeine so eagerly escapes into the organic solvent. This principle is not limited to caffeine. Extraction is one of chemistry's most versatile tools. It is sometimes called chemistry's Swiss Army knife. We use it to isolate natural compounds from plants, to purify the products of a reaction, to remove unwanted starting materials, and to obtain pure substances for medicines, foods, and flavorings. Many industries rely heavily on extraction as the very first step to obtaining a clean compound. There are two main types of extraction. The first is solid-liquid extraction, which you have probably performed today without realizing it. Brewing tea or coffee is a classic example. You start with solid leaves or grounds and add hot water. The heat gives energy to the molecules, making them vibrate and move faster, which helps break weaker bonds that hold caffeine and flavor compounds in the plant material. Those molecules then dissolve into the hot water. It is simple, but it is also chemistry in action. The second type is liquid-liquid extraction, which is the technique most often used in the laboratory. Here we work with two immiscible solvents, typically an aqueous layer and an organic layer. The compound of interest partitions itself between the two layers depending on its solubility preference. We usually carry this out using a piece of glassware called a separatory funnel, which allows careful mixing and then clean separation of the layers. How do we predict how much a compound will move to one layer or the other? Chemists use a number called the partition coefficient. Written as Kd, it is simply the concentration of the solute in the organic layer divided by its concentration in the aqueous layer. A large Kd value means the compound strongly prefers the organic solvent, which makes the extraction highly efficient. A small Kd value means the compound prefers water. This number takes the guesswork out of extraction and is crucial when designing experiments or even drugs. Now let us walk through caffeine's journey in the lab. We begin with tea leaves. The first step is steeping the leaves in boiling water. This is our solid liquid extraction, which transfers caffeine, along with tannins and pigments, into the aqueous solution. At this point, caffeine is in water, but it is not alone. In this first step, boiling the tea bags releases caffeine and many other organic compounds. Heat increases solubility, allowing molecules to move from the solid plant material into the liquid. However, because this solution contains not only caffeine but also tannins and pigments, we need to find a way to selectively separate the caffeine from everything else. Our second step is to add sodium hydroxide, NaOH. This is a strong base. It reacts with tannins and phenolic compounds, which are acidic, and removes their protons. Once deprotonated, these molecules become negatively charged ions. Charged species are highly soluble in water, so they remain trapped in the aqueous layer. Caffeine, by contrast, does not react with sodium hydroxide under these conditions. It remains neutral, and thus is free to move into another solvent later. This clever step chemically tags the impurities to keep them in water while leaving caffeine neutral and mobile. The tea solution, now containing caffeine and the ionized tannins, is poured into a separatory funnel. Dichloromethane is added, and immediately two layers form. Water, being less dense, forms the top layer, while DCM, being denser, forms the bottom layer. Caffeine now faces a choice, and because of its much higher solubility in DCM, it is ready to escape into the organic layer. Mixing the funnel increases the contact surface between the two solvents, giving caffeine molecules plenty of opportunity to cross the boundary. But mixing must be done gently. Solvents like DCM are volatile, so pressure builds inside the funnel. Venting frequently is essential to avoid accidents. At the molecular level, caffeine rapidly moves into the DCM, while the deprotonated tannins remain safely in the aqueous phase. One of the most common mistakes is forgetting to vent the funnel. The buildup of vapor pressure can cause the stopper to pop off, leading to spills or even injury. Proper venting, by inverting the funnel and carefully releasing the stopcock, is a key safety practice. This step highlights the power of solubility. Neutral caffeine molecules find the moderately polar DCM environment far more suitable than the highly polar aqueous layer. Polar tannins remain in water. This selective migration is the entire basis of liquid-liquid extraction. Another potential problem is forming emulsions, which are cloudy suspensions where droplets of one liquid remain trapped in the other. Vigorous shaking can cause this. Chemists fix emulsions by adding salt, often in the form of saturated brine. The added ions increase the polarity of the aqueous layer, forcing the organic droplets to coalesce and separate cleanly. This process is called salting out. Once mixing is complete and the layers settle, the lower layer containing caffeine dissolved in DCM is drained from the separatory funnel into a clean flask. The choice of DCM is ideal because its higher density allows easy separation from water. Even though DCM and water are immiscible, a small amount of water always dissolves into the organic layer. To remove it, we add a drying agent such as anhydrous magnesium sulfate or sodium sulfate. These salts act like tiny sponges, grabbing onto water molecules and forming solid clumps called hydrates. When the powder remains free-flowing, we know the water has been completely absorbed and the DCM is dry. The dried solution is then decanted or filtered to remove the solid drying agent. The next task is to remove the solvent itself. This can be done by gentle heating in a fume hood, or more efficiently with a rotary evaporator, which uses heat, rotation, and vacuum to speed up evaporation. What remains after the solvent is gone are crude caffeine crystals. There is also an important efficiency principle to note. If you have 60 milliliters of solvent, is it better to extract once with all 60, or 3 times with 20 milliliters each? The answer is 3 smaller extractions. Each wash allows a new equilibrium to be reached, pulling out more solute. This is just like rinsing a sticky cup multiple times. Multiple extractions always recover more of the compound than a single extraction. Crude caffeine may still contain impurities. To obtain pure caffeine, we recrystallize it. The crude solid is dissolved in the minimum amount of hot solvent, then allowed to cool slowly. As it cools, caffeine molecules arrange themselves into a pure crystal lattice, leaving impurities in the solution. Filtering the cooled mixture gives pure crystals. Purity is then confirmed by measuring the melting point. A pure compound has a sharp, well-defined melting point, whereas impurities lower and broaden the melting range. So from tea leaves to pure caffeine crystals, this journey reveals the hidden forces of solubility and polarity that control where molecules choose to live. Extraction is not just a trick for the lab bench. The same principles guide drug design, where the partition coefficient predicts whether a medicine can cross from the watery bloodstream into the fatty tissues of our cells. Too polar and it will not pass through membranes. Too nonpolar and it may never dissolve in the blood. Striking the right balance is often the difference between a successful medicine and a failure. Every cup of tea and coffee you drink is a small-scale example of this profound chemical principle. It is a story of molecular escape, of choices made at the atomic level, that shape industries, medicines, and even our daily routines.